These are really exciting times. Major breakthroughs are happening in neuroscience and in artificial intelligence, benefiting our everyday lives. In particular, neuroscience is making AI better, and AI is making neuroscience better. And so I will talk about the incredible innovations, opportunities, and also risks that are happening through these interactions. I myself, I am a neuroscientist. I study the human brain and how it relates to the behavior. My major tool for studying the human brain and predicting behavior is MRI, magnetic resonance imaging. We put participants in brain scanners, like you see on the screen, and we can measure their brain activity while they're performing different types of tasks. MRI has been around for a while. As you know, it's a very powerful tool to image internal structures in a safe and non-invasive way. Around 1991, scientists have discovered that you can use these MRI machines to infer neural activity while people are looking at things or thinking about different things. And that is known as functional magnetic resonance imaging, which I will call fMRI throughout my talk today. So I am basically an fMRI scientist, and I feel very lucky to be a scientist in this modern age, because for us, fMRI is kind of like having a telescope or having a microscope. Without a telescope, you cannot study the stars. Without a microscope, you cannot study the microscopic world. And thanks to fMRI, we can learn more about how the brain operates than ever before. You see here on the screen that, at least at the beginning, in the 1990s, people were using fMRI to infer what different parts of the brain do. However, now, in 2018, thanks to AI, machine learning, machine intelligence, and computational power, we can learn many more incredible things about what's happening in your brain while you're in the scanner. Let me show you a few examples. This study is not from my lab. This is from Jack Gallant's lab at UC Berkeley, but it inspired many projects in my laboratory. This is a study where, imagine you are a participant lying down in the scanner. You can see a TV screen when you're in the scanner, and you're watching this video on the left, okay? You're watching a video clip. And what Gallant's group did was that they built models using machine intelligence, machine learning. They built very sophisticated models to understand what is the relationship between when you're watching a movie and the brain activity that you can infer using fMRI. And then just based on the fMRI signals alone, while you're watching this movie, they can guess what you are looking at. And that guess is shown on the right of the screen. So let me go ahead and run this. Again, while you're in the scanner, you're watching the movie on the left, and on the right is a computer guessing what you are looking at. It is truly a form of mind reading. Okay, and this study was published in 2011, and so it's a fairly recent breakthrough in human neuroscience. In fact, this technology has been so well developed now that a group in Japan at ATI have also used this technique to scan people while they're sleeping and while they're dreaming, and they have been able to start to decode what people are dreaming as well. My own laboratory, Alan Cohen and Bryce Kuhl were members of my laboratory. They were so inspired by the study that you just saw that they decided that they wanted to try to advance the methods of mind reading. And they did this study where they wanted to see if we can draw what faces people were looking at in the scanner. So imagine you're in the scanner, you're looking at a face one at a time, and we can build models of how the face perception activates your brain. And just based on reading out and decoding that brain activity that's collected through the fMRI scanner, we can guess on the bottom, our computer can draw what faces it thinks that you were looking at when you were in the scanner. And although it's a little bit fuzzy, for a first attempt, I think it worked out pretty well. The match is about 65% based on what people were looking at in the scanner and what the computer is guessing based on the brain scans. Again, it is a form of mind reading. In a separate project, my own laboratory, together in collaboration with many fabulous colleagues, in particular Todd Constable's group at the Yale University School of Medicine, we are using this fMRI method to do other kinds of important discoveries about the human brain. And so this is a little different from what I just showed you, but let me try to explain what we did here. In this study, we put people in the scanner, and we did not necessarily ask them to do anything. In fact, we just had them lie down in a task known as resting state. We just asked people to lie down in the scanner and just rest. Of course, your brain is always active. Your brain is never idle. And importantly, everyone's brain is unique and operates in fairly different ways. And our big scientific finding, our development, is that we created a way to convert your brain activity to a spreadsheet of numbers. We were able to read out your brain activity during the resting state and convert it to a matrix of numbers, a spreadsheet of numbers. And importantly, that matrix of numbers is unique to each individual. It is something that we call the functional connectome, because what this set of numbers is measuring is how different parts of your brain are communicating with each other in synchrony or out of synchrony. But long story short, I can take each one of you, put you in the scanner, scan you for 15 minutes, and then I can pull out from your brain a matrix of numbers that will be unique to you. And so we're going to call that a brain fingerprint, and that's why for the cover of the journal where this was published, they have this big picture of a fingerprint. So imagine I can pull out a brain fingerprint from each one of you that's going to be unique to you. That alone is interesting, but what's even more remarkable is that there are components of your brain fingerprint, just like there are components of your genome, that correlate with different traits and behaviors. And so using that discovery, we published a finding showing that we can read out your IQ based on your brain fingerprint. Okay? Again, long story short, I can take any one of you, put you in a scanner, scan you for 15 minutes, and then my computer will tell me what your IQ is. It's accurate enough that I no longer allow my students to look at my brain activity. I don't want them to feel intimidated. Moreover, different components of your brain fingerprint correspond to different behaviors. For example, we want to use this technique to quantify behaviors that are difficult to change into numbers. For example, in this study, we can, just by scanning your brain and extracting your brain fingerprint, we can read out and quantify how attentive you are. We can quantify whether you have attention deficit disorder or not, and how severe those symptoms are. In other studies, we can scan Alzheimer's patients and determine how severe their memory symptoms are. We can quantify that. We can put an autism patient in the scanner and determine how much cognitive impairment that they are exhibiting. In fact, in another study, our lab can take people, put them in the scanner, and we can even read out their personality. We can determine how extroverted you are or how neurotic you are just by looking at your brain fingerprint measured with fMRI. So I'm pretty excited about a lot of these findings, and we'll talk about how they can be further used to benefit society. But I also want to take a moment to say that this was only possible because of the massive computational power that we started to enjoy over the past 10 years, and most importantly, because of the fancy and very powerful and exciting algorithms that artificial intelligence and machine learning are providing to us as they are providing to the world. And we are all already benefiting from these technologies. When you're looking for a book or trying to choose a song, the product recommendations you get from Amazon or from iTunes and so on are coming from machine learning algorithms, just as you might see in this example over here. The driving assistance systems or even self-driving cars is possible thanks to advances in machine learning and artificial intelligence. And the algorithms for image recognition are becoming so powerful that they even rival board-certified doctors in their ability to classify and diagnose skin cancers or other types of cancers that are measured through radiographs. In particular, of course, everyone in this audience in Korea is very familiar with the fact that artificial intelligence can now beat human champion Go players. And this is really, and I know it got a lot of hype and attention in the media. And what I can share with you is that it has not been overhyped. It is truly sensational. It is remarkable. I think it's one of the most important findings in modern society that a computer is able to beat a human at this remarkable game of Go. It is astounding. No scientist ever predicted that this could have happened this early in our lifetimes. Because the game of Go is so complex, and because even the most fastest, powerful supercomputer cannot explore all the moves possible in order to beat a human champion. Okay? It was only possible because they changed the way these algorithms worked. It was because of advances in neuroscience is why a computer was able to beat a human. And I would really love to credit Demis Hassabis, the CEO of this tremendously innovative AI company, Google DeepMind. He basically incorporated principles from neuroscience in order to create this massive advance in AI computing. And I'm a huge fan of him, and it's partly because, and I'd like to share with you here, is that he was a neuroscientist. His training, his PhD background was actually in fMRI research, very similar to what I did. And in fact, I might even say that 10 years ago, I was more famous than he was. But of course, things have changed a lot since then. He's done a lot more with his life than I have. But anyway, his training was in cognitive neuroscience using fMRI. And he used his insights, his knowledge of neuroscience, to bring these tremendous advances to artificial intelligence. And I'm very happy and grateful to him because he continues to advocate for this importance of this marriage between neuroscience and AI. For example, he published this paper where he talks about constantly that his artificial intelligence algorithms are inspired by neuroscience principles. And he talks about, with so much at stake, the need for the field of neuroscience and AI to come together is now more urgent than ever before. And he has the goods to be able to say this statement because AlphaGo, this remarkable algorithm, was able to achieve its revolutionary performance because of this marriage from neuroscience. So this is a beautiful image of neuronal cells in the brain. And the way to think about the brain is that you have all these, about 100 billion neurons. They're kind of like little simple computers, and they're massively connected through dozens, if not hundreds of trillions of connections known as synapses. And the most important thing to know about this massive connectivity, these networks of neurons, is that they communicate with each other, and most importantly, the connections are modifiable. Okay? And that allows the brain to learn pretty much almost anything it needs to learn. In addition, the neurons are not just randomly forming some kind of soup in your head, but they are organized into hierarchies, and they form layers. You can think of them as forming layers of different levels of sophistication and processing. So if here we have the brain on the top, and we have an artificial system on the bottom, a neural network, an artificial intelligence system on the bottom, brain schematic on the top. And the idea here is that you can take sensory input, vision, sounds, touch, and so on, and you increasingly process that to more sophisticated levels. At the beginning, you just process sounds and colors and lines. And at the end, at the other end, on the far right side, after you go through all these layers, you have meaning, you have words, you have concepts, you have faces and scenes, just more complex representations. And this is basically the architecture of how AlphaGo is able to achieve its remarkable level of intelligence. In addition, there are two principles of neuroscience brain processing, human brain processing and animal brain processing. There are two principles that make us humans so special, and they were incorporated by Demis Hassabis into his artificial intelligence algorithms. One is replay, which is the idea that even when you are not actively looking at something or thinking about something, even when you're resting, your brain is replaying its experiences. In fact, when you sleep, when you dream, dreaming is actually your brain replaying its experiences from the day. And it's not just doing that for fun. In the process of replaying its experiences, it's forming knowledge and it's forming memories. As proof here, we have on the top left some pictures of neuronal activity collected from a rat when it's running around in a maze during the day. And on the bottom are the same neurons essentially replaying its activity while it's sleeping, while it's dreaming. Okay? There's a strong correspondence. In fact, if you disrupt the dreaming, the rat's learning starts to go down. It becomes impaired. Next is prediction. Your brain, you can constantly plan and think about the future and think about the outcomes, potential outcomes of different actions and thoughts that you may take. And previously, computers really didn't do much prediction. But one of the reasons that AlphaGo can do its amazing things, as well as chess programs, is that it has this ability, built in this ability, to start to predict the outcome of different moves. So in sum, I think where neuroscience and AI have kind of a joint mission, joint benefit, is in providing personalized predictions for humans, for machines, for any objective that you may have. And there's still, exciting developments are just starting, they're just starting now. I think the next 10, 20 years are going to be incredible. We're going to see some amazing innovations that are going to benefit us all. And so we need to continue to think about how AI and neuroscience can inform each other. Number one, obviously, computers have more speed and power compared to the neurons in your head. However, humans are much more versatile. Our brain cognition, human brain cognition, is much more flexible, and it can adapt, and it can transfer learning much better than a computer can. You teach a computer one task, it's only going to learn how to do its one task. If you teach a human a task, it can usually generalize that to many other tasks. Second, computers have this amazing capacity to run simulations. Like we have to sleep and dream in order to do replay. You can program a computer to replay all the time. Okay? Right now, AlphaGo was trained on human games. The newest version of AlphaGo, it's called AlphaGo 0. It can beat the AI algorithm that beat the champion Isidore. The most current version teaches itself. It just runs on its own and plays with itself in order to achieve a remarkable learning and performance. That's something that computers can beat humans at, all the time because they're so fast and powerful. Whereas with humans, one advantage that we have is that we don't need all these training examples. We can learn just from one example. You teach a 2-year-old what a giraffe looks like. You don't need to show 100 or 1,000 pictures of giraffes. A child can learn and generalize in almost one shot. And that's something that AI algorithms are now starting to learn. How do you learn something so quickly in one instance? Once they start picking that up, then AI will become even more smarter than it already is. And then the third point is that computer algorithms and AI benefit and can process big data. They can process huge amounts of information. But they don't know what to do with that information. They don't know right from wrong. They don't know what's good or bad. And so ultimately, we always need a human teacher. We always need ethical control. We need a human to teach machines what is right or wrong. Okay? Because data won't teach a machine what is right or wrong. Here are some examples. This is a chatbot. And within a day of release, a bunch of human users were interacting with it by Twitter and taught it to be racist and evil. This chatbot, within a day, just because of bad data and interactions with humans, it started to deny the Holocaust, it started to love Hitler, and it became very racist because artificial intelligence algorithms, they don't know what's right or wrong. They'll just copy whatever data is being fed to it. There's a term for this, garbage in, garbage out. Okay? They don't have the ability to discern what's good or bad. Only humans can do that for machine learning algorithms. These are pattern recognition systems. These are congressmen in the United States, and a computer algorithm categorized them as criminals, having been in prisoners. And of course, there are these other very disturbing examples of misclassifications of human faces. And also even self-driving cars, we have to worry about how safe they are because again, they're not perfect, and they need to learn how to make judgments when they go down the road. Same thing for neuroscience. We're gaining this ability. I can read out your IQ. I can read out your personality. We ultimately want to use this for good. We want to be able to diagnose depression, mental disorders, reading disabilities. There are so many powerful ways to use this, especially in medicine, for good purposes. But we have to be careful not to use this for bad purposes. We don't want to be screening people without their knowledge for just certain jobs or certain schools. That would be terrible if you got into Yale because your brain scan looked good and you got denied admission to Yale because your brain scan looked bad. That would be terrible. So we have to make sure we use these new technologies in good ways. And same thing with AI. Again, AI does not know good from bad, and so we have to make sure we continue to have ethical control over our algorithms. And in closing, again, I think the biggest risk with all these neuroscience developments and with artificial intelligence is mental privacy. Okay, we should never use these techniques to extract information about individuals without their knowledge. If you're going to read out something from their brain, if you're going to read out something from their profile on social media or their usage of web traffic, then we should be telling people what information we're extracting from them. And so I'll close with this. I want to thank you so much for your attention, and I look forward to the future we have together in neuroscience and AI.